So we're talking last time about pressures on structures. I mentioned this one case, we talked about the comet last time. These planes that started never arriving at their destination because they would drop out of the sky. And the problem was they found out that the windows were square. It's very simple, as in many things, something quite simple. Windows are square. At the corners of the windows you have stress concentrations. You inflate the cabin backwards and forwards and you fatigue these, you develop cracks, and the windows blow out and you lose pressurization and you lose the plane. The other example that happened much more recently, I think this is 1988, as you can see from this, from Wikipedia, was in Aloha Airlines going between the islands, Hawaiian Islands, and again the same problem, not with the windows, I think, in this case, but with the roof, because it was making these 10-minute, 20-minute flights, inter-island flights, up, down, making, 20 a day, multiple pressurizations and depressurizations, salt air, fatigue of the aluminum body. All of a sudden, the roof, I think, not the thing you want to see in a plane, right, when you're flying, the roof unzipped, and I'm pretty sure some people were taken out. I also remember that some flight attendants were grabbed onto by the passengers, and the plane landed amazingly. You see. So it's an amazing workhorse in terms of the structure of the thing and the redundancy, I guess you could say in this particular case, that it was able to survive. But the reason that we're talking about fluid pressures on structures, gas pressures, gas is a fluid, and obviously it's a type example perhaps of what we're dealing with here. Okay, so that's just to give us some idea of what's going on. So let's continue then with that motivation of saving lives. With what we were doing last time, and as is our tradition, we'll kind of recap what's going on. So you recall that last time we talked basically about the idea that we could have a structure and we could look at, this isn't a dam, but we could look at the pressure distribution behind that structure. And really we didn't get much further than this last time to physically derive this expression, which says something about, very important expression, which says something about the force that's applied to the structure, and it really is just an integration of this pressure distribution. And we went through it last time, I won't go through it this time, but if you take the fluid pressure at a point and multiply over the area that it's applied, then you end up with an expression which ultimately ends up being this. So a very important expression. Very important to remember what the components are. This is the area of the plate which the fluid pressure is applied on, which in this case is this area here. The difference between y1 minus y2 multiplied by the width, which I guess isn't on here. I think we used last time. HC is the depth of the centroid. So for this particular plate, the centroid, as we said last time, is the point of balance of that plate. And so the depth of that in this particular case is, I guess, y1 over 2, right? So in this particular case, this is h sub c, which is, in this particular case, is y1 over 2, because this is the water surface in this particular case. All our derivations were relative to that. And importantly, this height is the vertical distance, vertical depth. And so you see this, if you have this figure, you basically have it drawn here. It's the point where the centroid is relative to the free surface, because the fluid pressure is increasing from 0 at the free surface to whatever it is at that point. And so the basic idea is if you know the fluid pressure at this point, multiplying it by the area gives you the force that's applied on that plate. That's purely and simply what that expression is. Incredibly simple expression, but incredibly general as well. You can always use it. And the unit weight is the unit weight of the fluid you're using. 9.81 kilonewtons per meter cubed for water, and a thousandth of that roughly for air. It can be applied both ways. The plate at the bottom of this figure, by the way, obviously has a fluid pressure acting on the top, which is acting downwards, normal to the plate. And it also, if it's just sitting in water, has exactly the same fluid pressure acting upwards, perpendicular to the plate, and therefore it's in equilibrium. And so that's not really the interesting structures that we're interested in. We're interested in structures where we have different fluid pressures on either side because it's a container of something. We didn't talk about this, but this is a straightforward law that you can imagine if you have a horizontal vector, and if you have a vertical vector, then the resultant of those is just by Pythagoras, right? is just the vector sum, I guess. So the square of each one is just this triangle, right? So it's basically this triangle of two lengths. This is FV, this is FH. Squared gives you FR, which is the resultant, which is straightforward. And so the one question we haven't answered yet is, where do they act? And so that's what we'll spend today doing. And so the very simple explanation of where they act is, we said there are three things you should know last time. One is you want to know the magnitude of the force. This is FR, the resultant, we know how to do that. The second is, we'd like to know where it acts, because knowing the magnitude of the force and where it acts says that you know something about the loading of the structure. And then with that, typically we want to be able to use that to say something as to whether it collapses, whether the gate opens, etc. And so the second thing we need to know is exactly where it acts. And so what we can do is we can take moments about a point. So what we can do is we have this pressure distribution here, which is this area here. If we integrate that, we get FR, which is given by this magnitude here. And so what we'd like to do now is find out exactly where it acts. So what we can do is we could take moments about any point. Doesn't matter where they are. And just for convenience, let's take moments about the surface in this particular case. And so what we can write is, if we look at the moments about the surface, we can write this expression here. That the moment about this point is equal to the lever arm multiplied by the magnitude of the force. Nothing more than that, right? This is the lever arm, this is the force, and if you want to counter that, you have to apply a moment that does that. If you do that, then it will be in equilibrium. So this is the expression that we have here. And so what we could do, we can write this about any point we choose. We could write it here or here, but we're going to choose to do it at the surface. And if we do that, we can rearrange this expression like this. And if we have this expression, then if we know what FR is, all we need to know is what the moment is, if we can calculate it, and we have some way to be able to calculate this location. So that's what we're going to do. I won't go through it in excruciating pain or detail, but otherwise to say that in the past we took the fluid pressure at a point and multiplied it by an area and then integrated that over this area. So what's a moment? How does a moment differ from a fluid force? A fluid force is a pressure times an area. A moment is a pressure times an area multiplied by a lever arm. And so we can get the moment by doing exactly what we did before, but by, instead of multiplying it by just nothing, by 1 in here, we multiply it by lever arm. If we substitute for the fact that the fluid pressure here is given by the unit weight times the depth, which we know, then we end up with this expression here. And so if we have this expression here, and we know already what the force is, then we can just look at the ratio of those. This is just the moment divided by the force. Obviously that's exactly what this says anyway. And if we take this expression for the force and put it on the top, and we take this expression for the moment and put it on the bottom, sorry, the other way, this expression for the moment and put it on the top rather, this expression for the force and put it on the bottom. The unit weights cancel out, so we don't care about those, but this is exactly the expression that we do. And so what we could do with that, let's see if I have enough space to be able to do this. So you'll never have to do any of these derivations, let me assure you. You need to know how to use these things. So I'm going to see if I can limit myself to my little games to within this little contour. So here we have. So this is the expression we have. We have lever arm, it's equal to this. So what's the integral of y squared dy? It's going to be equal to a third y cubed between y0 and y1, right? And I suppose we could also multiply that by w. And we're going to divide that, well, we've already done this one, right? This is going to be a half y squared integrated between the same limits times w. And there is a reason for doing this. And so, if you like, we can write this as y1 and y0 if it makes you feel better. y0 is 0, right? It's at the origin. And so this is just going to be y1. And so let's call this just y, y1, y, so we just don't have to keep on writing it out. And so let's write it out in longhand. And I could write it as, there's a reason for me writing it this way. A third y squared times y times w, right? It's no different from this. I'm just taking the y cubed and writing it as y squared times y. And I'm going to take the bottom and I'm going to write that as a half y times w. And the reason for doing that, of course, is that this is the area of the thing. Not of course, but that's the reason. And so let's continue on this merry journey. So if this is a third here, then I can also multiply both top and bottom by 4. And if I do that, I can write a third as 4/12. Seems stupid what I'm doing, but bear with me. And I want to just keep the bottom as it is, half y yw. And if I can write it this way, then I can also split this expression up to being 1/12 times y squared yw plus 3/12 y squared yw. Intriguing, isn't it? Has this guy lost his mind? What's he doing? And the bottom hasn't changed. The denominator hasn't changed. It's y yw. And what else do I want to do? Okay, so the very last segment of this is that I'm going to write this as, again, a 12th y cubed times w. This is 1, which seems just collecting terms, plus, so how am I going to write this? I'm going to write this as a half y all squared yw, and I'm going to yes, okay. And I'm going to write the bottom as yc times a. So this here is a. This here is the depth of the centroid. So this is equal to this point here. This is y sub c. And in this particular case, so why is that the case? The third y squared. And so in this particular case, this first term here is what I will call IXC over YC times A. And I'll add to this area. So this is what? This is 3/12 is equal to a quarter. So hence this term here. A half squared is equal to a quarter, y squared. And this is just equal to a times yc squared, right? This is yc squared, and this is a. So, pain over. The point is that we can always get the depth. You can certainly get the depth of this resultant just from using this expression straight away without any manipulation. This would be correct. But all we've done is we've taken it from this to look like something else. And the reason we've made it look like something else is that this term here is a standard result. It's called the second moment of area about the centroid. And in your physics classes, you might remember things like expressions like this. So the centroid of this plate is this point here. If you look at taking this plate and it being this, then the balance point is the centroid, if it was rigid. But if you have, and the reason the balance point is the centroid is that every single piece of this paper weighs exactly the same, and so the lever arm it has against this point is balanced exactly around this axis here and this axis here. If instead of having a uniform thickness, the thickness was graded, so it increased from a big magnitude here to a negative magnitude here, then the lever arms of those are different, and the balance point, the resultant location for that balance point for that lever arm change. And so physically what that means is that we can use the second moment of area about the centroid. So this here, if you can't see this, this is IXC. So this refers to the fact that this plate, you're rotating about you're taking the moment about the x-axis, which in our case would be the horizontal, right? This is our coordinate system. In this particular case, remember, x is horizontal, y is vertically downwards, but it can also be inclined. It doesn't have to be vertical. Has been in our derivation, but it doesn't have to be. And so we're looking at the rotation of this around that axis. So this is the second moment of area in the x direction relative to the centroid. So to centroid. Whoops. So hopefully you've seen this before. So rotation around the x-axis. And this term here refers to the opposite, right? So this is the rotation this way. This is the rotation this way. So we want this one, right? Because the fluid pressure is increasing with depth. And so you can imagine a triangular distribution on this that's pushing on this plate. And so the place where the center of pressure acts isn't the centroid of this. It's below it. It's the center of pressure. And so that's why we want to be able to use this. So don't worry about the derivation. Remember, this is a standard result. And for some of you, you'll be happy to understand where it comes from. But just to make the point again, it's nothing more than saying we can calculate the location of this point if we know what the moment is and the force, because if we know this and this, the only unknown we have in this expression is this. And so all we've done is basically done that and done it with a bit of calculus. So the important expression in this, to go back to this, are these expressions here. The most important one is this one here, which we've just derived. This is exactly the expression that we have here, that we've derived, and it's written out here. So what we did was we took this result here, which was this, and we split it up into two parts. We split it up into two parts because it allows us to use this standard result, for which we have an expression, 3 pages on from this, and also some information on this. And so it really becomes something that's plug and chug. So we said there are 3 things to know. Magnitude of the force, we know how to calculate that. It's this top expression. We want to know where it acts. We now know how to do that. And then if we know that, we can say something about the stability of structures, which is the third part. Okay? Very important, this stuff. The other important thing to remember about this is that for these expressions, remember that we have the magnitude of the resultant is equal to unit weight times the depth of the centroid times the area. Very specifically, this is the depth of the centroid. It's not the magnitude of y. So the depth of the centroid is the vertical distance in the direction of gravity, if you like, between the free surface where the pressure is 0 and the centroid of this plate, which is the balance point of this plate. When we do the calculation for the location of where the force acts, which is y sub r would be acting somewhere here. And so let's just draw that on here. It typically is not the place, but the important thing is that this y is actually measured in the plane of this. So if this is vertical, then y is the same as the vertical distance, which is the same as the way you're measuring h. But if it's inclined, then it's the intersection of this with the surface, which is really what this is showing. So this is my attempt to draw this figure. This is the top of the fluid. The top of the fluid has the y equals 0 axis. So this here is y equals 0. This x is along the plane, so x, y, z, this is it, right? So this is the coordinate system. X is always, the y equals 0 axis is always at the fluid surface. The plate might be at the fluid surface, it's just how we've done our derivation, but this expression is entirely general. The plate could also be down here. But the coordinate system always has to be at the surface. So those are the key points. So remember, depth, distance along the plane, to the centroid, to the center of this plane. And I won't confuse you, well, yeah, no, I won't confuse you, but we'll maybe note it, sorry. Let's do an example. Should cement this idea. So here the idea is you've got a hole in a wall, you have a plate which has a hinge on it, and that hinge is free to rotate, and we'd like to be able to know whether we can use this as a gate, and the idea is that the gate might have a hinge here at half height. It has fluids both sides. If you empty the fluids out of this side, then what force is being applied at here to be able to stop it from rotating? The other thing, so before you go on, the other thing that this tells you as well, it's perhaps easier to look at this expression here, the depth where this resultant acts is equal to the depth of the centroid plus something. It always is either at the centroid or deeper than it. And the reason for that is that the fluid pressure is increasing with depth, and therefore you can imagine there's a bigger weight given, physically a bigger weight given to the deeper fluid because it has a bigger pressure than the stuff above the centroid, which has a smaller pressure. And so that's why in this figure I specifically drew y sub r below this. And if you like, if you want to think about this expression in a different way, this is y sub c. So I guess this other magnitude here is the extra length, IXC YCA. I know I'm talking in jargon, but so this length here, by definition, has to be the second moment of area about the centroid divided by the depth of the y coordinate of the centroid multiplied by the area of the plate. Just the area of the plate. So the area of the plate is this ringed portion, this red portion here. Right? So that's it. So let's go back to this. So we need to know Jake. Some of you know who Jake is. Must be Semi or Jonathan looking at that stuff. All right, so here's the idea. So centroid of the plate. Where's the centroid? Well, I don't have a saucer to balance on my finger, but you know from common sense, well, from your own personal knowledge, but also from standard results, that the centroid of a disk is the very center. Well, you know that the second moment of area about the centroid is given by this expression here, both in the x and the y direction. This is the axis we were interested in, the horizontal axis. And so it's this one, which happens to be pi r4 over 4. So we'll use that when we go back here. I haven't gone back? Oh yeah, there we are. And so we want to calculate where this acts. The centroid, the center of pressure, which is where it acts, C of P, is going to be equal to the depth of the centroid, which in this case, what is it? It's a 10 meter diameter plate that's 10 meters below the surface, so YC is equal to 10 meters. The depth of the centroid here is also equal to 10 meters. It happens to be vertical, so it's the vertical distance from the surface. And this coefficient here is pi, radius of the plate, to the power 4 divided by 4. Always the units of this moment of inertia have to be in units of area times length squared, which is really what this is. So it's always units of length squared. So this is IXC, second moment of area about the centroid of the plate. The area you can get from pi r squared, where r is equal to 5 meters, and the rest is plug and chug, and you end up with an expression which gives you the depth of the centroid, which is this, 10 meters, plus the offset. And the offset, I guess, is 0.62 meters. That's it. Always works, always works. And so you know that the centroid of this system, I can't get them both on at the same time, there I can. So you know that the center of pressure in this particular case is 10.62 meters down from the top. So what, you say? Well, we'll use it for something useful. Okay? You could also do it for the second moment of area in the y direction. So now, if you wanted to, you could look at not only this plate twisting about this axis here. So if this is the plate twisting about this, you could also look at it twisting about this axis. It's not useful for this case, so, because we don't need it. But if you wanted to know where the center of pressure was, so now you know that the center of pressure is somewhere along this line. That's all you know. If you wanted to know exactly where along that line is, then you would use this expression. This is equal to 0, as it turns out, if you just look at the standard result. I think they probably have it written down here. I won't zoom in. Oh, yeah, we'll zoom in. So this is equal to 0. This means that it's, because the pressure distribution is increasing with depth only, then basically, whoops, each side of this disk sees exactly the same effect of the pressure distribution, and so there's no net moment in twisting it around this vertical axis, which is the y-axis. That's physically what that means. And so that means that the location of the centroid, I need to go up one more, right, is actually at the x equals 0 point, which is this point here. So you know it's exactly there. So you know not only the depth of it, yr, but you know the magnitude of, it's at the centroid of the plate. The place where the plate would bounce if you put it on your finger. Your first finger, obviously. And so we have that, and we want to know what the magnitude of the force is. Well, that's very straightforward. Unit weight we know. The depth of this happens also to be y sub c, right? Not this depth here, but this depth here. This is also hc equals yc in this particular case. Doesn't always. And if you do the math for that, you end up with a magnitude where you use the area as well, and you have this. And you end up with a force. So we have a force and a point of action. So we've done the first two of the things that we'd like to do. We want to know what the force is, that's what we said, we just happened to calculate it last. And we want to also know what the magnitude, where the point of action is, the center of pressure, which is y sub r and x sub r. And we've done both of those. And so we know exactly where it acts. And so the third part is to do something useful with it, not just to calculate that magnitude, but see whether the gate opens. So this is the geometry we have, right? This is the pivot point. This distance here is 0.62 meters. And so now we want to know, if you drain out the water from this side, what happens to the gate? Well, we have to have a little stop here, right? So as we drain this water level down until it's out of the picture, then we only have fluid on the left-hand side. Now, instead of arbitrarily taking a location that we've take our moments around, which is really what we did here, right? We said we could take our moments around here or here, it didn't matter. When we want to look at failure, this is a very important point, you have to describe a failure mode. The failure mode for this would be that this will physically rotate, the plate will rotate in this direction, and this will kick out. And so the failure mode for this would be it pivots around the pivot point, and if the force here isn't big enough to resist that, then it will let the water out. And so the question is, what's the force that this little stopper has to apply to be able to solve that? And so the calculation is pretty straightforward. It's going to be what? we just take moments about this point, and if you do them clockwise, it's going to be what? The magnitude of FR times, in this particular case, the location of the resultant minus 10 meters, right? Or if you like, 0.62 meters is this magnitude. Has to equal this force of the stopper, if you like, multiplied by the lever arm. The lever arm is the radius of this, which I think is equal to, well, we've called it R, but it's equal to 5 meters, right? And I think if you do that calculation, well, it's just down here, then you end up with a magnitude that you have to apply, which is this. So that's basically it. So that's it. So you don't have to derive those things, but you do have to be responsible for magnitude of the force, unit weight, depth below the free surface to the centroid of the plane structure, and the area. That expression, by the way, only works for plane structures, flat plane structures. It can be this, it can't be this. It doesn't work for this. Okay? So that's the other point. So it doesn't work for a curved structure. Okay? All right, so we'll use those principles again. So what else? Well, we've done this derivation. That's what we've done. Let's try, you want to try another one? How do we do this? Very similar example. Everyone okay with that, by the way, first? Right? Okay. So, very similar question. Bit contrived. You have a gate here, you have a water on the left-hand side. The question is, what is the magnitude of this force, P, that you have to apply to be able to keep that gate shut? How'd you go about doing it? Well, now you need to be able to calculate the magnitudes of the resultant forces acting on here. And you can imagine, I suppose, that there would be, that's not very straight, right? If you do this, and if you look at pressure changing with depth, then certainly the pressure at this point would be 3 meters of water, so it doesn't start at 0. And so the pressure distribution would be something like this. And there are a couple of ways you could do it. You could divide this up into two prisms and take moments, or you could use the method we've just used. I think we'll use the method we've just used. So what you want to do is you want to calculate the magnitude of the resultant that acts on here in the horizontal direction, and you want to calculate its depth. And so the magnitude of the resultant is equal to the unit weight, the depth of the centroid, times A1. So the unit weight is water. What's the depth of the centroid? Center of this plate is going to be HC1, which is going to be right in the middle, which is going to be 3 meters plus 2 meters. So that is 5 meters, if I'm not wrong. HC1. So that's this. And the area of the plate is going to be 4 meters times 3 meters into the page, or into the board. Okay? There's going to be a pressure acting on the bottom. The magnitude of this resultant, I think F2 in this particular case, or F resultant 2, is going to be the unit weight of fluid, the depth of this centroid times the area. Depth of this centroid is 3 meters plus 4 meters, which is 7 meters. The area is 2 meters long, 3 meters into the page, so this is equal to A. So we have the magnitudes of each of these two plates. And you see this little diagram here. We need to know where it is, and so for this one, you know it has to act somewhere in this plate, so it has to be on the plate somewhere. And so the YR for this one, if you like, is going to be in the plate, at the depth of the plate. But I think in this case you want to actually know where along this plate it's going to be, because you want to ultimately take moments about this point here. So if it's a fluid pressure that acts uniformly on this plate, the actual center of pressure will be exactly the same as the centroid. Right? because the fluid pressures are uniform across it. It's the seesaw that balances this, if you like. And so you can imagine if you have that fluid pressure weight acting on here, the balance point of this is the centroid of this, which is also the center of pressure. And so the magnitude of this length here, where this acts, is going to be equal to 1 meter. Right? It's not so easy for this one. We have to do this calculation. And so the calculation for this one is this. First moment, the second moment of area about the centroid, depth of the centroid, the y component of the centroid in A1. So the second moment of area about the centroid is this expression here. Right? This is the plan of the plate. So this is the width. Our plate is 3 meters wide and it's 4 meters tall. This is B, this is A. So it's 4 times 3 cubed divided by 12. That was the expression we had in the derivation we did. So 1/12, 4 cubed times 3. The depth of the centroid we had before is 3 meters down plus 2 meters down, which is 5. And the area of the plate is just this. And the depth of the centroid is 5 meters. So it's saying that the depth of this y sub r, L1, is equal to what? There's 3 meters. There's 3 meters here to the surface, and then this magnitude L1 in this particular case is going to be equal to 2.27. There's a point in there, right? So this is y sub r from this running out of space to do this, but this is y sub r. And so we have this location. And so what we can do is now we have the magnitude of F2, the magnitude of F1. We know where F1 and F2 act. And so we have everything to be able to solve that. So what we can do is now we have to write moments around a specific failure mode. And the failure mode is a hinge here that this is pushing against, and the water is pushing from this side. But there are 2 components of water pressure, horizontal water pressure and also this push downwards, which is trying to physically rotate this out from underneath us. And so we just take moments around here. So if you take them counterclockwise, anti-clockwise, counterclockwise, L1, F1, so what is it? Plus L2, F2, we know L2 is equal to 1 meter, has to be equal to, what's this height? It's 4 meters, is it? Times P. P is a force, uppercase P. And so we certainly know what these forces are because we've calculated it from resultant force is equal to unit weight, depth of the centroid below the surface multiplied by area for each of these. And we also know individually what the lengths are. We know where this force is going to be applied, and so the only unknown is the magnitude of the fluid pressure or the force that we have to apply. And it turns out after you do the math, it's this. So that's it. Okay? So you can apply it universally. We can do things in slightly different ways as well. The other way to do these things, so we've done them using this expression, but the other way, for some examples, it's much simpler to do this, is to just know some standard results and to do the calculations based on those very straightforward standard results. And so one way to do that would be to know, for instance, that if it's a plane surface that intersects the water table or the fluid, then you can calculate the resultant again by using the same expression we had before, unit weight area times the depth of the centroid, just by realizing that this is the depth of the centroid, this is the unit weight, and this is the area. And the standard result is this half gamma h squared b. And so you can get the magnitude of this. And you also know that the center of pressure acts 2/3 of the way down. And the reason you know that, of course, I said I wasn't going to confuse you, but maybe I lied, is that you can do this nifty little game. And if you think about the distribution of the fluid pressure acting on this gate, then this is the fluid pressure distribution that's acting on that. If you think about this, the balance point, ignore the fact that I've doubled this over and has double thickness. Think of this as a single thickness cardboard triangle. The balance point for this is 2/3 of the way down from the top and 1/3 of the way up from the bottom. And so really this second moment of area that we're talking about that gives us the location where this force acts is actually the balance point of this pressure distribution, right? Which is kind of a curious thing. So it's not a big point, but it's just a curious exposition of how math is really quite wonderful, right? In terms of giving closure to all these, or mechanics is quite wonderful. But basically the point of action of this force is really the balance point of the pressure distribution around a fulcrum. And of course that makes kind of sense, right? Because we've been summing moments about something, and so the moment due to this pressure distribution on the left side of this fulcrum, balanced with the larger pressure distribution with the shorter lever arm on this, gives this the balance point at this point here, right? It balances. And so that's what it is. And so what you can do, if you want to, is you can always, if you know these standard results for this triangular distribution, you could, for instance, break down the pressure distribution on an inclined plane into two parts and do the moment calculation, right? So this is the distribution. You can break it down to a prismatic part where you know the point of action is in the middle. You can break it down into a triangular part where you know the point of action is 2/3 down and 1/3 up. And if you know this length and this length, which we've just said, if you calculate the forces due to the green and the red, and you know the sum of these two forces is equal to the resultant, then you can calculate where the lever arm is as well. And you may have done that in some of your classes.